Alright, so this is Griffiths Electrodynamics problem 2.26, and this is a rare, I guess, preview of the problem, or it's sort of an addendum, except I'm putting it at the beginning of the video. So basically I made a mistake, and the mistake I made was I used the letter rho here when I should have used Q. So I need to go back and rewatch the video, but I'm pretty sure I probably just kept saying charge density when I meant charge. So this needs to be the infinitesimal charge element. Alright, and so that applies throughout the video. So when you see this rho, just think of it as a dq. I think I'm also did that up here. So yeah, just a heads up, just make this quick little change here so I don't have to redo the entire video, because it takes 20 minutes or something like that. So, alright, so this is Griffiths Electrodynamics problem 2.26. We have an ice cream cone, Griffiths calls it, but the thing it's a rather wide ice cream cone, so it's as wide at the base, well, twice as wide at the base as it is tall. So the radius of the base, or drawn at the top in this case, is the same length, h, as the height of the cone. And what we want to do is find the difference in the electric potential between points A, here at the vertex, and B at the center of the base. So what we're going to be doing is using this equation here, the potential, we have our 1 over 4 pi epsilon naught that we see all the time, and then we'll just be integrating over the charge density, and then the distance, the magnitude of this cursive r, which is just the distance from the source point to the field point. Now one thing to keep in mind when we're using this equation is this assumes that the potential is set to 0 at infinity. So this equation won't work when there is charge out at infinity. Griffiths goes into this, that your integrals will diverge and bad things will happen. So so that prevents us, because the potential is set at 0 at infinity, that prevents us from just saying, oh, well, let's just define the potential to be 0 at A. So what we have to do is calculate the potential at A due to this cone. By the way, this cone carries a surface charge density of sigma. Alright, uniform surface charge. Alright. So yeah, what we have to do is find the potential at point A due to this uniform surface charge on this cone, find the potential at B, and then just subtract them to find the difference in potential. So yeah, don't fall into the trap of just like, oh, well, let's just set the potential to be 0 at point A or whatever. Alright, so looking at our integral, in this case, well, let's just dive into this. Let's start with point A. So what we want to do is we really want to find out what this cursive r is. And what that means is at every point in our integral, we want to know how far away we are from this point A. You can do this using different variables if you want. I'm going to just integrate along z. I'll use z as the variable of integration. Z just being let's call 0 at point A, and then going up to z equals h up at here at the base of the cone. Alright, so if I were to zoom in just at the edge, so let's let's zoom in at a spot like right here, okay? So I'm going to just take a slice of this cone, all right, and the height of this slice, which would be the same on either end, obviously, is going to be dz. All right, I want to know what this dl is, because this is the piece that actually has the charge on it, and these are obviously not the same length. All right, because our piece of charge, right, our rho from up here, you know, maybe I should make this a differential since we're integrating over rho. Our rho is going to be, let me write it this way, equal to sigma dl. Right, so here's the, again, sorry, I should write this as a differential. All right, so our little piece of charge is the surface charge density multiplied by the length. And I guess I also need how long this strip is going to be, right? Because this strip, if I'm zooming in on this little piece, it actually will be a hoop that goes all the way around this, this cone. So what I need is another length as well, also to make the units work. So the length of the circumference, right, is 2 pi multiplied by the radius. So let me just throw that out here. Now we need the radius of this, and it's going to be anywhere we look at on this cone, because this height is the same, or sorry, this length for the height is the same as the length for the radius up here. This is just a right triangle with two legs the same. It's isosceles, right? So the radius is going to be the same as the height up, which is z. We're coming up from 0. So if I, sorry for messing up the picture, but if I were to zoom in right here, then we'd have z right here and z right here as the radius. These are really tiny, hard to see, so hopefully you can see that. All right, long story short, short story long, we have a z right here. That's the radius, 2 pi z times dl times sigma. That's our d rho. So since I'm going to be using z as the variable for my integration, I need to find dl in terms of dz, and just using Pythagorean theorem, I get, you know, you memorize the 45, 45, 90 triangle, right? So you just get a square root of 2 multiplied by dz. So let me make this nice. We have a 2 times the square root of 2. We have a sigma, we have a pi, we have a z dz. Okay. Probably didn't have to go through all that, but it's good to make it clear. So now what we want to know is this curly r, or the cursive r. All right. So let's just do that over here. What is this cursive r? So if I'm, again, we're focusing at point A right now, at the vertex of this cone, and if my little dl is right here, then cursive r is just the distance between A and dl. So which is just, if we're up at height z, again, this picture is getting messy, don't worry about the picture, I guess, but again, if we want the length of the hypotenuse of this 45, 45, 90 triangle, then it's just the length of one of the two equal sides multiplied by the square root of 2. So we get a square root of 2 multiplied by z. Okay, so this is the length of r for of this cursive r for our first part, which is finding the potential at A. So let's put these pieces together real quick. So I'll call this V sub A. We've got our good old 1 over 4 pi epsilon naught out front. Now we need to plug in our d rho and our cursive r. And since I'm using z as the integration variable, we're going to integrate up from z equals 0 all the way up to the top. The cone is height h, so we're going from 0 to h. Okay, so plugging in this d rho, we've got a 2 square root of 2 sigma pi z dz. Now we plug in our cursive r here on the bottom, which we found was square root of 2 times z. Okay, our square root of 2 divides out, and our z divides out, so that's a really good, very convenient truth for our integration. Now, what do we have left over? We have a 2 sigma pi, and then we're just integrating just this dz from 0 to h, which we just get h. All right, so I believe, let me make sure I did this right. I think I did this right. Yeah, so here is our potential at the point A. So now let's look at point B. This one's going to be a little bit more tricky. Obviously, the other one was too simple to be the simpler part, if that makes any sense. So looking at part B now. So we have to re-evaluate especially this cursive R piece right here. Okay. So our infinitesimal piece of charge, though, is still the same. All right, so let me just write that out again. 2 square root of 2 sigma pi z dz. So now we come to the unfortunate step of finding our cursive R for this piece. So if I'm looking again at the cone, something like that, and right here is my little piece of charge that I'm focusing on. Now we're finding this piece right here. So this distance from point B up here down to our charge is our cursive R. And what is this in terms of z? Well, we can form a triangle right here. This side of the triangle right here, we already talked about is z, because we're up z from the radius on this. These are all similar triangles if we take the little cross section, or a slice through the cone, I guess. So if we're at height z, then this side will be z, and this side will be h, this total height minus this z piece down here, so h minus z for this side. So that gives us this cursive R squared is equal to z squared plus quantity h minus z squared. So multiplying this out and stuff, let's see what we get. We have, we'll get a 2z squared minus 2hz, and then we have a plus h squared. Okay, and I'm going to put this under a square root. So now, just to solve for our cursive R, so now let's write our integral again. This time we've got VB. All right, so we have our good old 1 over 4 pi epsilon naught out front. We are integrating, again, we're going up from z equals 0 up to z equals h. Oops, started writing a z. Okay, and plugging in our infinitesimal piece of charge, right? 2 square root of 2 sigma pi z dz, and then on the bottom 2z squared minus 2zh plus h squared under square root. So really the integral that we have to do, all these are constants, right? They come straight out. And we've got this z over 2z squared minus 2zh plus h squared. Forgive me, I have sinned. I just put this into Wolfram alpha, and it did the integration for me. If you're hardcore, you can work it out by hand. So what did Wolfram alpha give me? Let me just write out the indefinite integral. Okay. So after putting this into Wolfram alpha, we get a 1 over 4. And then this is probably not enough space to write this. I will do this in 2 lines maybe, so yeah, so just be aware of that. Let's see if we can do this. So we have a 2, we have our h squared minus 2hz plus 2z squared, all under a square root. And then, let me see how much left I have to write. A bit. Okay, I'm going to write this down here. So plus the square root of 2h. The h is not under the square root. Then we have a natural log of square root of 2, and then a square root of h squared minus 2hz plus 2z squared. This is all under a square root. And then down here so 3 lines, great. Minus h plus 2z. Okay, I think I wrote that right. Alright, and then a plus an arbitrary constant. Alright, so we are going to be evaluating this integral at the limits of 0 to h. So yeah, sorry for the mess, but we'll be writing it out a couple more times, at least I'm sure. So, alright, I'll write it out again really quick. We have a 1 over 4 pi epsilon naught. Now we have all of our pieces in here. 2 square root of 2, we have a pi, we have a sigma. Okay, and then we have this thing. Let's go ahead and evaluate this at our limits of integration, which are h and 0. So plugging h into this, we get a 2h squared here on this term, and we have a minus 2h squared of this term. So we just get the square root of h squared, so just an h. Let me go ahead and bring this 1/4 out front so we don't have to worry about that. So here we have a 2h for this first term. Now we're plugging in h for this other part here. So we have a square root of 2. We have an h outside the square root. We have a natural log. And alright. Again, this term, it's that mess under the square root, same as up here, we just get an h. So we have a square root of 2h. And then we have this minus h. And then this z, we plug in an h for that too, so it's a plus 2h. Okay. All right. Okay, so now we are going to have our second limit of integration at z equals 0. So minus, plugging in a 0 here, we get a 0. So looking underneath this square root, I really hope this is visible enough on the video. Looking underneath this square root, we have a 2hz that goes away, and this goes away too. So again, we have just an h squared under a square root, or just an h. So we have this time a minus 2h, and then a minus, we get the square root of 2h natural log, and now we look inside the brackets here. Again, this stuff under the integral just gives us an h, so we have our square root of 2h, and then we're putting in a 0 for z once again. So that term goes away and we are left with just a minus h. All right, we're getting closer and closer to having the second part of the problem done, and then we can finish off this problem. 1 over 4 pi epsilon naught. We have, let's look at this really quick. Okay, so this 2h minus an h, that'll just give us a plus h, so I'm just going to write that as plus h. What else can we do? Gee, we could factor out this h, can't we? By the way, this minus 2h here will cancel with that 2h up there. We factor out a square root of 2 and this h. So this square root of 2 will combine with this square root of 2 and give us 2. And then that gives us 2 times 2, which is 4, divided by this 4. So all of that will go away. We still have our pi, we have our sigma, and then we have this h that factors out. And let's see how fast this can go. All right, now let's look at our natural logs. Let's just combine these two, right? So using our logarithm rules, we can write this as one natural log, where I probably don't need this bracket or brace thing anyway, where we have, let me just write it out in full real quick. Square root of 2h plus h divided by this square root of 2h minus h. There, I did it. Okay, now both top and bottom of this can be divided by h. So I mean, it kind of depends on how far you want to take this. You can, I'm not going to take it all the way. I'm just going to, so once I divide by h here, the h will go away and we get a square root of 2 plus 1 and a square root of 2 minus 1. I'm just going to multiply by square root of 2 and call it good. So 1 over 4 pi epsilon naught, we have our pi sigma h natural log. So multiplying, let me just take these out. Okay, so multiplying by square root of 2, I get a 2 plus square root of 2 and a 2 minus square root of 2. All right, so, you know, we can simplify this further probably, but I don't care. All right, I think what we've got here is our potential at point B. So I forget what Griffiths asked, if we want A minus B or B minus A. Let's write that right here. So let's just call it delta B equals, let's do B minus A. So we go around, we grab our VB up here, but there are some things we can factor out, looks like, if we want to. Let's factor them out. 1 4 pi epsilon naught will be the same in both of these. We also have a sigma, we have a pi, and an h. And now we're doing b minus a. So all we have left here is the natural log of 2 plus square root of 2 over 2 minus square root of 2. And then we're subtracting this guy off. And all that we have left on this, after we factor out this stuff, is just a 2. So we get a minus 2 right here. So this may not be the final form that Griffiths gets, but so this is the difference in the two, the difference in electric potential from point A to point B, or point B to point A, whatever. Toss in a minus sign if you need to. But here's the difference in potential between those 2 points.